afternoon, ladies and gentlemen. It's a pleasure to speak to you at this session. I'll just share my screen now. And we'll be talking about innovative APV technologies and designs. So what we believe is that for APV design, a scientific approach is needed so that you can prove the bankability and improve the benefits for both developers and farmers. So we have a 6-pronged strategy for doing that design. And that's the number one is having elevated structures, utilizing the synergies between solar and agriculture, having light simulations and microclimate simulations to understand your growing environment, and then having agriculture models that are adapted to that environment. And then lastly, having a robust water management strategy that takes care of this whole agriculture design. So to start with, we'll talk about a bit about the light simulations. Now, crops utilize the visible spectrum of solar radiation, which is also called the photosynthetically active radiation. Now, apart from the location of your project, the geometry of the project will determine how much light is reaching different parts of your ground. So the tilt of your panels, the ground coverage ratio, and very importantly, the height of the system as well, because that determines the homogeneity of the light, is going to determine the amount of light that reaches. Now, different types of crops require different light. So you have grains like wheat, rice, maize that require a lot of light, like 40 to 50 moles per meter square per day. And then you have some trellis growing crops like tomatoes, capsicums that require 20 to 30 moles, green leafy vegetables like spinach and lettuce that needs less light, even less light at 10 to 15 moles. And then a similar amount is needed for rhizomes growing under the ground like ginger and turmeric. So based on what you want to grow, then you need to design the geometry accordingly, or vice versa, depending on what your constraints are and how you want to optimize it. And then the light simulation will give you the distribution of light on the ground, and it will not be totally uniform. So although your goal is to utilize all the land well, and you want to do have as homogeneous light as possible, it won't be totally homogeneous. So there'll be different light at different parts of the ground, and you want to use that information to determine your cropping layout. Now, the solar panel shade also has a very significant effect on the microclimate of crops. So the microclimate of a farm consists of the air temperature, the soil temperature, humidity, and the wind speed. And this microclimate can have a very big effect on very important physiological processes like the rate of photosynthesis, the timing of flowering, the nutrient absorption via the roots, and the quality of the fruits, because too much heat would cause sunburn. So I'll use this infographic to show you that how important it is to measure this temperature, because it will be different under the shade, and that has an effect on the crop growth. And in India specifically, there are very high temperatures in the summer, which actually create a loss of productivity. So the shade can actually be used to your advantage to reduce that temperature and affect growth positively. So if you look at this infographic, on a bright sunny afternoon, 37 degrees centigrade, the different surface temperatures will be very different under shade and without shade. So you have a tree here with some shade. Now, if you look at this on the green grass without any shade, the surface temperature is 42 degrees, whereas under the shade, it's 31 degrees. So you can see how much effect it can play. So now if we combine, these whole simulations and create, a flow chart on how we should design it. So you have your inputs or the outputs coming in from your microclimate simulation and the light simulation. Now you feed that to an agriculture database that you should create. Now that database will have all information of a variety of crops, right? So what kind of soil they need, what temperature they need, how much light they need in different phases of their growth. So you have all this information with you. Then you have, for your site, you take the simulation of the microclimate and the light, and then you compare that, right? And then based on that, you select your crops. Once you've selected, or a preliminary selection of the crop, then you run that through a crop yield simulator like STEEX or DSSAT, and you get what the crop yield can be at that. From that, you get your crop revenues. So now this would be an iterative process, because once you do that, then you go back, you can see, okay, if I change my design a bit like this, what's the change in the microclimate? What's the change in the light? How does that affect everything? Can I change my crop here? And then I see what revenue I can make out of it. So you can go through this process iteratively to design it. Similarly, on the solar generation side, because here we have a system which is not like a single surface, you can use the simulations to actually get your average albedo and then feed that into a PV sys to get your solar generation and solar revenues. So this way, this whole approach then gets you much closer to having bankable revenues and cash flows, which can help you finance the projects. Now, based on these design methodologies, what we have designed what we call an APV shade house, which is basically a combination of an elevated solar structure and a shade net house. And shade houses are they're established things. So it's not because they cost a lot of money. So not a lot of them have been done in India, but the economics are well established and it's a common thing. So we have designed such a shade house, APV shade house, using cable stabilized lightweight structures, retractable shade nets, and are doing horticulture farming below them. Now, just quickly, cable structures, because the cost of APV can be high, right? Because you have all these elevated structures. So you want to minimize that cost, and cable technology is one way of doing that. So you could have different, you can have longer spans so that you have lesser foundations in your field at lower costs. So you can have like a 5-meter span, a 10-meter span, or a 25-meter span with cable structures, and they'll all be cheaper than rigid systems. And these are all projects in India that have been done using cable structures here. So now one of the most important aspects is to utilize the synergies so that you can generate more revenues, lower your costs, and create good economics. So the first thing that is the structural synergy, right? So you have to elevate your panels just so that you get more homogeneous light anyway. So you need a good height of 3.5 meters to do that. Now, when you're doing that, then why don't you just use the structure to support shade nets as well, to support a trellis system so that you can grow crops vertically and utilize that whole space below the panels. Then there's the PV generation can actually increase as well, and we'll talk more about that in a subsequent slide. Then the operations and maintenance synergies. So you can use the same water for panel cleaning and for the irrigation. And also the labor synergies, because now you have a lot of farm labor in the field, and that labor can be used for cleaning the panels as well and other O&M activities. Then a given is, the civil infrastructure. So the solar project comes with, good lighting, fencing, land grading, storage. So all that generally is not available in India to, in agriculture farms because it costs. So all this infrastructure is used by the agri farm as well. And then we should never forget the social aspect of it. It would generate a lot of social local employment. It would improve the acceptance of solar projects in a lot of areas. And also, as the Kusum scheme envisages, the electricity that is generated can be used in agriculture feeders and have more distributed energy at megawatt scale. So now we'll talk just a bit about the generation aspect, because that's a very important aspect of this. So in this shade house, we have, illuminate shade nets. Then on the ground, you have crops growing, you have reflective mulches. On the walkways, you have reflective weed mats. So there's a lot happening there. And generally, agricultural soil has a low albedo of about 0.5, 0.15 to 0.2. But with this whole APV system and all these aspects, you can have an albedo of 0.3, 0.35, which is kind of almost double of that of the bare soil. Then also you have, because for the light, you have more gaps between the rows, and you have higher elevation. So all that combines to give you a much higher bifacial gain, which we believe could be up to 2 times the bifacial gain what you would see in a ground mount. Then the other aspect is the temperature. So obviously we know that panels will generate more electricity if the temperature is lower. Now the evapotranspiration from the crops lowers the temperature. In a study done in Arizona, which has very high hot climate like in India, and very dry climate there as well, there was a study done where they observed that the panel temperatures were up to 9 degrees lower in the summer months, which is huge in terms of PV generation. So all these combined, it can have a big effect on the generation. So now if we take all of this and try to take a look at the incremental economics of APV, which is, I guess, the bottom line, then here's the numbers. So on the left, I have some of the design specs listed for which these numbers are being mentioned. And then it also includes all the agriculture infrastructure, like the irrigation systems, the shade nets, and crop monitoring systems. So the incremental capex of such a system would be about 60 lakhs. So this is per megawatt. So the incremental capex per megawatt would be 60 lakhs more than a conventional ground mount. However, the additional power, because of what we discussed on the previous slide, could be about 4 to 5, and this assumes bifacial panels, would be about 4 to 5% more power generation. Now, on the agriculture side, and these economics for shade net agriculture is kind of established, right? So all over the country, there are several examples, and we've done surveys to figure out how much revenue profit they're making. So you can, for 1 megawatt, which we're saying is about 4 acres, you can generate about 25 lakhs of revenue, which is 15 lakhs of profit. So 15 lakh per megawatt profit from agriculture with 4 to 5% additional power generation, you could get an incremental equity IRR of 5%, which means if your ground mount equity IRR is 12%, we're talking an additional 5%, making it 17%. So that's what we believe is possible through this. We'll be very soon setting up such a shade house. By the end of this year, we'll have a couple of projects set up with this, and we'll get real data from it. And just to kind of round this up, there are many agriculture strategies that can be done, which will benefit from such an environment. And one such is a model that we have experimented with is called additive intercropping, where you're growing multiple crops on the same land at the same time. And things like these can even further improve your agriculture income. So that's kind of it. Just wanted to put one slide of what, as Sunseed, what do we do? So we're doing project design and consulting via partners providing full turnkey EPC services, and most importantly, doing farming operations, because developers usually don't want to get into farming. So we'll do the farming operation for you. So that's the end. Thank you so much. I'd like to work with everyone to kind of realize the true potential of APV in India. Thank you.